Okay, thank you, Julian, for the introduction, and also thank you for the invitation. And it's my great pleasure to speak in the seminar. So yeah, so today I will talk about equivariant K-stability and the corresponding equivariant valuative criterion for the K-stability. So before I start my talk, let me first of all talk about the settings throughout my talk. So I will mostly work on we will basically work over the field of complex numbers. And so when I say a Q-Fano variety, it's going to be a normal projective variety with mild singularities. And for those of you who are familiar with the singularities from the minimal model program, this is going to be the Kawamata log terminal singularity or KLT singularities. And so a Q-Fano variety have the anti-canonical divisor to be Q-Cartier and NPO. Okay, and we'll also work with a more sophisticated notion, which is the generalization of Q-Fano varieties. So we will also work with the log-Fano pair. So this is a pair, so a variety with a boundary divisor such that the log canonical divisor is Q-Cartier and NPO. And again, we can also define singularities on the log-Fano pair. And again, we want the pair to have at worst KLT singularities. So again, it's the singularities from the minimal model program. All right, and I will usually denote n to be the dimension of the variety X in the question. All right, so now let me talk about some of the motivations about the study of K-stability. So at first, as long as I know, I think it comes from the question in the differential geometry side. So it's about the Calabi problem, about the existence of K-line symmetric, which is where the Ricci curvature is a multiple of the Kähler class. And then we have the famous Yao Tandonison Conjecture. So we have the condition which is analytic about the existence of the K-line symmetric. And then Tian first proposed some notion about K-stability, and then Donaldson actually reformalized it as an purely algebraic condition, and he called it K-stability. So the Yao Tandonison conjecture states that the existence of K-line symmetric is equivalent to K-poly stability of a Fano manifold. Okay, so and this is proved by Tandonison Sun and Tian separately a couple of years ago. So for the smooth case, the YTD conjecture is solved. All right, so however, this K-stability condition is actually quite complicated. So it's defined through degeneration, C-star equivariant degenerations, which we will call test configurations, as we will see in the definition later. So this condition actually is very hard to verify in concrete examples. For example, even for the simplest case, for the projective space, we know it's Kähler-Einstein because we have the Fubini-Studi metric. And we can verify that it's a Kähler-Einstein metric. But if we want to check whether it's K-poly stable or not using the original definition via degenerations, it's actually quite hard. It is not direct. It's not very direct to see why the projective space is K-poly stable. Okay, so this tells us actually, so in reality, this definition is really hard to work with. Okay, then we have this notion of equivariant K-stability. So for a variety with some sort of symmetry, we can try to work with the equivariant version of everything. So we can work with the equivariant test configurations, as we will define later. So if we have a group action on the variety, we can look at a smaller class of test configuration with the induced group actions, which we will call it equivariant test configurations. Okay, and then in reality, checking equivariant K-stability will usually be easier, and we'll see examples later. So the projective space is a very typical example. The projective space has a lot of symmetry, And we also see some examples of Fano threefolds, and we also see other examples as well. So checking equivariant K-stability is usually easier. All right, then we have this conjecture, which tells us that equivariant K-stability is actually enough because for Q-Fano varieties with a reductive group action, if it's equivariantly K-semi-stable or equivariantly K-polystable, then in fact it's already K-semi-stable and K-polystable. So if this conjecture is true, so it'll help us to it'll help us with a lot of examples. When we consider examples with symmetry, we can just check equivariant K-stability, and then using this conjecture, we can deduce that it's already K-stable. Yeah. All right, so some progress about the conjecture. So right now, this conjecture is completely solved. So the history is that the first case solved is the smooth case, which is solved by data Ezekiel. The method they use is purely analytic, and it's actually inspired also by the solution to the YTD conjecture in the paper of Tandonison and Sun. Okay, so the smooth case, so for the Fano manifolds case, this solution is purely analytic originally. And then we have the solution for the torus action. So if the group we consider in the question is a torus action, so originally in Li Shi's paper, they proved the K-semi-stable case. And then in Li Wangshu's paper, they showed this conjecture for the polystable case as well. And in their paper, the method is purely algebraic, and it works for not only the smooth case, but also for the singular case. So we can allow KLT singularities in the question. So, and we also have the generalization of the result as well. It not only works for Q-Fano varieties, it also works for log-Fano pairs as well, if we try to generalize the result. Okay, and then in my joint work with Yuchen Liu, we work with the finite group action case. And again, the result works also for Q-Fano varieties, so not just for smooth case, but our method is kind of half algebraic and half analytic, because we'll see in the proof as well. So we actually use some results from the analytic side, which is a recent result about the solution to the uniform YTD conjecture, which states that if a Q-Fano variety is uniform K-stable, then we have the K-line symmetric on this uniform K-stable Q-Fano variety. And also, I want to mention, like, I think in February, the full YTD conjecture, even for the singular cases, are already solved in, I think in Liu, Yuchen Liu, Chen Yangxi, and Ziwen Zhu's paper, where they completely solved the question about the existence of the K-moduli for Q-Fano varieties. They give we have the projective K-moduli, and a byproduct of their result is, in fact, the generalized YTD conjecture for the singular Fano variety case. Okay, so finally, the full case for the conjecture, equivariant K-stability conjecture, is solved by Zhuang, I think not long ago. I think it's sometime last year. So he solved the general case. Basically, he given a purely algebraic proof for the conjecture for arbitrary group action and for singular Q-Fano varieties as well. Okay, so now we know that the conjecture is already true. Okay, so but in my talk today, I probably want to focus more on the finite group action case. And I will also talk about, so although our result is already covered by Zhuang's results, but still there's some So some of the argument in our proof can still be applied to some examples. We'll see later that can deduce the K-stability of some examples of qubit hypersurfaces. Okay, so before I talk about examples, probably let me first try to go through the definitions of K-stability and equivariant K-stability. So therefore, I need to go through the definitions of test configurations. Okay, so a test configuration of a Fano variety X is a C-star equivariant degeneration of X. So outside the central fiber, it's C-star equivariantly trivial. So it's X cross C-star over C-star. And then we have a degeneration over A1. So in the central fiber, for the degeneration, it can be anything. It can be, the central fiber can be very bad. It doesn't have to be reduced. It doesn't have to be irreducible. So in fact, usually anything can happen in the central fiber. And if the central fiber happens to be a Q-Fano variety, this is going to be a very good class of test configuration, which we will call special test configurations. And special test configurations, in fact, plays a very important role in the study of K-stability of Fano varieties. Okay, so this is the definition of a test configuration. And then if we have a group action G on X, then we can talk about the concept of equivariant test configurations. So first of all, if we have a G action on X, we can induce a G action on X cross C star. So outside the central fiber of the test configuration, we have a natural induced G action. So on any fiber over C star, so on the fiber over T, we first of all use the C star action on the test configuration to move this fiber back to the fiber over 1. Okay, and then we apply the G action on X. So we consider the fiber over 1, X cross 1, to be X itself, and we look at the G action. So we take the G action on X, and then we move this point back to the fiber over T. Okay, so we have this conjugation about moving the fibers. And so we conjugate the action of G by this C star action coming from the test configuration. Okay, so this is how we give this action G outside the central fiber of the test configuration. Okay, so if we have a G action on X and we have a test configuration, we always have an action outside the central fiber. However, this action might not be, we might not be able to extend this action perfectly to the central fiber. So in fact, in the case where we can actually extend this action to the whole test configuration, such that this G action actually commutes with the C star action coming from the test configuration, then we will call this test configuration to be G equivariant. So in a lot of cases, we don't have we cannot extend this G action so that actually the G action commutes with the C star action on the central fiber. So in this definition, actually, outside the central fiber, the G action always commutes with the GM action. So the question is whether we can still have this commutation of the action on the central fiber. So in a lot of cases, it doesn't have to be true. So therefore, in fact, usually we indeed have a smaller class where we look at G equivariant test configurations. So we throw away a lot of test configurations which we don't have G actions on the central fiber, which commutes with the GM action. Okay, so this is the definition of G equivariant test configurations. So before I move on, any questions? All right, then I want to talk about the definition of the generalized Fujita invariant, which allows us to define K-stability. Okay, so the definition of the generalized Fujita invariant I want to mention here is through intersection numbers. So we have this intersection formula for generalized Fujita invariant. So in order to do intersections, so I want to compactify the family. So I want to get a family over P1 instead of over A1. So I want to compactify the family over the infinity. So we can do that actually naturally. And in fact, G cross C star equivariantly. So this compactification is very natural because outside the central fiber of the test configuration, we see that the family is equivariantly trivial. So therefore, if we look at another family that is, if we look at another family over A1, which is trivial, we can glue the two families together over X cross C star, and then we get a family over P1. Okay, so this is how we can actually compactify the test configuration. And then we can do intersection numbers on the on this test configuration, on the compactified test configuration. And the formula is a little bit technical, but yeah, so this generalized Futaki invariant is the invariant we want to use, and the positivity of which is going to give us stability, K-stability of the Q-Fano variety we consider. Okay, so this is the intersection number, which computes the Futaki invariant. And I also want to talk about the norm of a test configuration, again, through intersection numbers. So there are a lot of, there are actually quite a few norm, the definition of the norm of a test configuration, and all of them are equivalent, meaning that if the norm is 0, the test configuration is going to be trivial. And the one I want to talk about is the non-Archimedean norm, which first is defined, I think, in Buxan, Hisamoto, and Johnson's paper, where they use non-Archimedean methods to study test configurations and K-stabilities. And so this, again, a little bit technical, but this is the definition of the non-Archimedean norm of a test configuration, where basically we look at a common resolution of the test configuration in question and a trivial family, X cross P1. And we look at a common resolution, and we do intersection numbers by pulling back things, by comparing polarizations and intersection numbers on Y on the common resolution, and we get this non-Archimedean norm. And if this norm is 0, we can deduce that, in fact, it's equivalent to saying that the test configuration is trivial, meaning that it's a product, and the C star action on the test configuration is also trivial on the fiber. Okay, so yeah, as I mentioned, this is one of the several equivalent norms of test configurations, and this norm is necessary when we try to define uniform K-stability. Okay, so now I think we are in a good place to define K-stability. Okay, and maybe I also want to mention that, so in all the definitions, if I take the G action here on X to be the identity group, then we recover the usual test configuration. We recover the notion of all the usual K-stability. Okay, so so therefore almost all the definitions of K-stability and equivariant K-stability are parallel. So X, we call X to be K semi-stable if the generalized Futaki invariant is non-negative for any test configurations. And if we want to consider the equivariant version, then we consider only equivariant test configurations. Okay, so this is semi-stability. And we call it K polystable if first of all, if it's K semi-stable and the Futaki invariant is 0 if and only if the test configuration itself is a product. And it's also, I also want to note that here, the test configuration itself to be a product doesn't necessarily mean that the test configuration is trivial, because even if it's a product, we can still have some C star action on X. So if the C star action is not trivial, we still don't consider it as a trivial test configuration. So a trivial test configuration is trivial if and only if it's a product and the C star action is trivial. Okay, so then we have the notion of uniform K-stability. So basically here we have a uniform lower bound. If we have a uniform lower bound of the generalized Futaki invariant over the norm, then we call X to be uniform K-stable. And if we want to consider the equivariant version, we consider equivariant test configurations.
Sorry, let's have a question for this uniform stability. Don't you need to consider something like infimum of this norm on kind of the twisted actions by the elements of the group?
Pardon me, please.
Yeah, so in your definition of uniform stability, you just took the norm, the J norm, the non-Archimedean norm, but it's more natural perhaps to take infimum over twists of your test configuration by generators of the group action. That's what Chi Li, for instance, does.
Yeah. So yeah, exactly. So I think my notion of uniform G equivariant K-stability is definitely not equivalent to what Chi Li does. Yes, I think what he does actually is more natural. Actually, I think I would say his definition is I think the better one. But yeah, at first when I tried to define this uniform K-stability, I was trying. I'm just trying to mimic, trying to define things parallelly with the usual K-stability definition. So so that in fact I will also discuss later. So that basically my argument of the valuative criteria can work through. But I think my definition here is in fact is stronger than these definitions. So his definition definitely works in a more more like general setting, definitely.
Well, maybe the point is that we expect existence of, let's say, constant scalar curvature to imply.
Yeah, exactly. Yeah. I think in my definition here, I'm not thinking too much about about its correspondence with the YTD conjectures about the existence of the canine symmetric, but more or less it's trying to produce a parallel result with on the analytic side about the original evaluative criterion were developed by Fujita and Li. Yeah, exactly. And I think, yeah, definitely. I think also later, I think right now, I think it's this in Li's paper, the definition there right now, I think they call it the reduced uniform K-stability. I think it's kind of a generalization, and I think it's already also proved that it's equivalent to K-poly stability. So it's kind of trying to work with. So for if we forget the equivariant version, originally the uniform K-stability, we know that the automorphism group of the variety is finite. So if we want to allow a continuous part in the group in the automorphism groups, so if we look at the reductive group action, so yeah, so the definition in Chi Li's paper is definitely the correct version to work with, and eventually I think in Liu, Xu, and Zhang's paper, where they prove the properness of the K-moduli, they show that this version of the uniform K-stability, actually, the equivariant uniform K-stability is in fact equivalent to K-poly stability, just as, which is a similar argument why uniform K-stability is equivalent to K-stability. All right, so yeah, as I mentioned earlier, if I take the group action G to be the trivial, the identity group, then we recover the usual K-stability notion, basically. All right, so now let me try to go through some examples. So first of all, let's look at the projective space. So as I mentioned earlier, we have the Fubini-Studi metric on the projective space. So by the YTD conjecture, it's K-poly stable. However, it's not uniformly K-stable because the automorphism group of Pn is not finite, it's PJLN. Okay, so we have a lot of symmetry on the projective space. So if we take the automorphism group, G to be the automorphism group of the projective space, then we will see that the projective space is actually uniformly G equivalently K-stable. We actually don't have G equivalent test configurations basically here. Okay, so yeah, so this way we can also then apply the uniform K-stability conjecture, the equivariant K-stability conjecture. So uniform G equivalent K-stable implies G equivalent K-stable, and then G equivalent K-poly stable, and then apply the equivariant K-stability conjecture. We can see that the projective space is K-poly stable. So this is another way of proving that the projective space is K-poly stable. And we also see from this example that the K-stability conjecture is not true for uniform K-stability. So maybe let me go back very quickly about the statement of the conjecture. So the conjecture only works for K-semi-stability and for K-poly stability. And this is as far as we can go. So the projective space provides a counterexample if we want to work with uniform K-stability. Okay, so this is the example about projective space. And then I also want to talk about the example which is considered in Chalsov and Shramov's paper. So in their paper, they look at, I'm going to follow their notation. So in their paper, they look at this class of Fano three-folds of degree 22. So they denote that class by V22 star. So for the Fano three-folds in this class, we have a C star semi-direct product with Z mod 2 action. Okay, and they computed G equivariant alpha invariance of these Fano three-folds. So I'm not going to define alpha invariance and G equivariant alpha invariance in my talk, but let me just mention that these invariants are in practical very useful to test to characterize test configurations. And in fact, we have this is what we call tense criterion. If the alpha invariance is greater than dimension over dimension plus 1 of the variety, we can deduce that the Fano variety we consider is going to be K-stable. And we also have an equivariant version of that as well. Okay, so for this class of Fano three-folds, they computed the equivariant alpha invariance, which is 4/5. So it's greater than 3/4. Okay, so then if we use the equivariant tense criterion, we can say that they are uniformly G equivariantly K-stable. And then if we apply the equivariant K-stability conjecture, we know that they're actually K-Einstein or K-poly stable. Okay, so this is another example where if we consider equivariant K-stability, the question becomes simpler. So in a lot of cases, computing equivariant alpha invariants are simpler when we have symmetry. And also in this case, if we try to directly compute alpha invariants, the alpha invariants are not big enough for us to apply Tian's criterion directly, but the equivariant alpha invariance is actually large enough. It's larger than the usual alpha invariant. Then we can apply the equivariant Tian's criterion to get eventually K-poly stability of this class of Fano threefolds. Okay, so this is another example where passing the question to equivariant K-stability for varieties with large symmetry, things we have an easier life usually. Okay, so the last example I want to talk about is about finite covers. So this is actually the example actually we consider when I first start talk about this question with Yuchen about Q-Fano varieties with finite group action. Okay, so if we look at this hypersurface in Pn defined by the equation x naught to the power of k minus f, and f is a polynomial of degree k in the variables x1 to xn. Okay, so for this hypersurface, it has a degree k cyclic cover to Pn, and this degree k cyclic cover is branched over hypersurface in Pn minus 1 defined by the equation f. Okay, so this example actually is already considered in Devon's paper when he considered K-stability of cyclic finite covers. And in his case, he's mostly considering the cyclic cover where the branch locus is in fact Yao. So when k is equal to n, the branch locus B is the canonical class of B is trivial. And in his paper, he showed that if the branch locus B is smooth, and if we have a cyclic cover to Pn, then we can deduce that X is in fact K-stable. Okay, and then we can generalize this result in our papers. So if K is smaller than N, then we have this branch locus B to be Fano. And as long as we know that the K-stability of the branch locus B, then we can deduce the correspondence K-stability notion of X. And maybe I also want to mention that we actually expect, so one of the useful case here is when K is equal to 3. So if we look at cubic hypersurfaces, so right now I think, first of all, right now we have the new result by Yuchen Liu, where we have K-stability of smooth cubic fourfolds. But originally, when we first start to consider this question, we only have the result about K-stability of cubic threefolds, which is the result of Yuchen Liu and Chen Yangshi. Okay, so therefore, if when k is equal to 3, we can use the K-stability of cubic threefolds to deduce a special class of the K-stability of a special class of cubic fourfolds here. Okay, right now we have, so basically this is more like an induction. So we have, if we have K-stability of cubic threefolds, we can deduce some special class of K-stability of some special class of cubic fourfolds. Now, because we have K-stability of smooth cubic fourfolds, then in dimension 5, when we consider fivefolds, for this special class of cubic fivefolds, we can deduce that the corresponding K-stability of these cubic fivefolds. And because we also have the openness of K-semi-stability and K-stability locus, so therefore we can conclude also that a general cubic fivefolds or a general cubic fivefolds is K-semi-stable here. Okay, so this is another example where if we can look at the equivariant, if we work with, we are actually here using some of the arguments in our proof to show that when we have a finite cover, so in this example, we are using cyclic cover, but if we have a finite cover, it doesn't have to be cyclic. We also have some results about K-stability. Okay, so yeah, so I think this is the examples I want to talk about for the where we have the usefulness of equivariant K-stability. Okay, so next I want to talk about the valuative criterion about K-stability. So the K-stability notion is quite hard. And also, even for the definition of equivariant K-stability, again, we need to look at degenerations of X. So therefore, people are trying to have a more algebraic and also with some of the criterions that people are more familiar with. So if we just look at the information on X itself, we have this valuation theory where we can get, in fact, K-stability through this valuation theory on X. Okay, so now if I look at prime divisor E over X, so we have a model here, a birational model Y, a birational morphism from Y to X, and E is a prime divisor on Y. And this is how, this is the setting where we call E a prime divisor over X. Okay, as long as we can find a birational model over X, so that in fact, this prime divisor is in fact, indeed a divisor on the birational model. Okay, so then I can define, first of all, the log discrepancy of this prime divisor. So this log discrepancy is just the coefficient of the divisor E in the relative canonical divisor ky over kx. So it's the coefficient plus 1 of the divisor E inside the relative canonical divisor. Okay, so this is how we define the log discrepancy, A sub x E. And then we also have this quite technical definition of the invariant S of E. So we have this integrals of this volume. So the volume function is continuous, so the integral makes sense. And when the X, so basically here we are look at sections of vanishing order X along the divisor E. And if X is very large, is large enough, then we know that we don't have sections anymore, so the volume will be 0. So therefore, the integral is in fact finite, and the upper bound is tau of E. So this tau is called the pseudo-effective threshold. So the upper bound is where we still have sections of vanishing order T along E. Okay, and so this number here, S of E, is in fact, if we rewrite it in another way using integration by parts, we can see that this in fact is somewhat a way of expressing the expected vanishing order of the sections of negative x, kx, with the expected vanishing order along E of the sections of negative kx. Okay, so basically the derivative of the volume can be viewed as the probability density function. And then we have the formula basically for the expectation of a random variable in probability theory. So this is going to be the expected vanishing order basically. But that's not very irrelevant, but this is just the formula for the definition for this invariant S of E. Okay, and tau of E is the pseudo-effective threshold, which is the upper bound of the vanishing order where we still have sections. Okay, then we can define the invariance, which is considered in the valuative criterion. We have the beta invariant of E. For each divisor, prime divisor over X, we can define the A of E, which is the log discrepancy minus S of E. Okay, so this is the beta invariant, and we also have the J invariant, J of E equal to tau of E minus S of E. And I also want to note that from the formula here, we know that so this volume is always less than or equal to the volume of negative kx. So the whole integral is, if we put this scale inside the integral, the whole integral is always less than or equal to 1. So therefore, this S of E is always less than or equal to tau of E. So this J invariant is always positive. And the positivity of beta invariant actually is going to be relevant to K-stability. Okay, so now let me state the evaluative criterion. This is a result developed by Fujita and Li separately. So a Fano variety X is called is K-semi-stable if and only if beta invariant
technical problem.
Any question?
You got cut at some point. So what you are saying that you are stating the theorem?
Oh yeah. So I see that it seems my internet just disconnected for a while. It's like a little bit unstable. So yeah, I think it's okay right now, right?
Yes, it is. Yes, it is. It works.
Great. Yeah. So this theorem is developed by Fujita and Li separately. So for K-semi-stability, we look at beta invariant for any prime divisor E over X. So as long as the beta invariant is non-negative for every prime divisor over X, then we know that the variety is K-semi-stable. And for uniform K-stable, we look at the fraction beta over J. And if we have a uniform lower bound for beta over J, then for each prime divisor E, then we have uniform K-stability. Okay, so this is the evaluative criterion for the usual notion of K-stability. And this actually, this theorem is quite influential because after the evaluative criterion is developed, I think the algebraic side of the algebraic side progress of K-stability actually moves quite fast. Like a lot of theory is developed after these evaluative criterion in the last couple of years. So this is really yes.
Yeah, I have a question. This delta in the theorem, the delta in the theorem is the same as the slope of the uniform stability?
Yes, exactly. In fact, in the proof, basically, yeah, let me also talk very briefly about the proof. So basically, for any prime divisor E over X, we can construct a test configuration from this divisor. And if we compute the generalized Futaki invariant and the non-Archimedean norm of that test configuration, we will see that it indeed is a multiple of beta and J. Therefore, the non-negativity of beta, in fact, comes from the non-negativity of the generalized Futaki invariant. And this inequality beta of E greater than or equal to delta J of E, it indeed comes from the definition of the uniform K-stability. Exactly.
And sorry to interrupt also, but can you address some remarks about the relationship with the slope stability, I mean, of Ross and Thomas a long time ago, compared to this valuation criteria?
Oh, yes, I think if I remember correctly, there's
they were considering test configuration, if I remember well, with respect to the normal cone.
Yeah, exactly. So one of the equivalent definitions for the slope stability is where we consider only test configurations coming from the definition to the deformation to the normal cone, where we blow up basically subvarieties on the central fiber of a product X cross A1, and we look at the again we can define the Johnson-Futaki, the generalized Futaki invariant there, and then if we only focus on this smaller class of test configuration, we get this notion of slope stability. So it's in fact so therefore K-stability implies slope stability, but still I think in fact there are also some relation, some work on on this relation as well, which also involves, I think, birational superrigidity as well. So I think there's one paper by Odaka and Okada where they state that if X is birational superrigid, they deduce that X is slope stable. And in fact, their results can be strengthened later. In fact, first of all, we have a conjecture that birational superrigid Fano varieties is K-stable. So this is the conjecture, and I think some recent results states that this is a result by Stibitz and Zhuang. I think they put some condition on the alpha invariant of the Fano variety, and then they deduce that if X is birational superrigid and the alpha invariant, I think is if it's greater than 1/2, we can deduce that X is K-stable. So yeah, I think there's also some history in the study about the relation between slope stability and K-stability, but yeah, I think there's they're definitely not equivalent. So just considering test configurations from definition to the normal cone is not enough for K-stability, but the notion of slope stability itself is definitely also of interest as well. All right, so this is the valuative criterion. So I think maybe I want to move a little bit faster. So yeah, let me just double check. So my talk should end at 50, right? Okay, yeah, so now maybe I want to just talk about this, the equivariant valuative criterion right now. So if we have a group action on X, okay, so then we can define a class of pseudo-valuations where first of all, we can take any element G, small g inside capital G. We can act this G on the valuation by composing any function on X with the action of G. Okay, so then if we take the infimum among all the action on the valuation, we get a pseudo valuation, which we will denote by capital G dot B. Okay, so this is this pseudo valuation we are going to replace the pseudo valuation in place of the valuation coming from the prime divisor in the original evaluative criterion. And basically we can produce a parallel result. Okay, so we can still try to form the ideal sheaf, which actually examine the vanishing orders of functions on X, where we take the intersection of all the ideal sheaf of the vanishing order of the ideals coming from regular functions of vanishing order of X, and we take the intersection among all the elements inside the group, and then we get this ideal sheaf, and then we can define a corresponding invariance as well here, as in the usual evaluative criterion. We can so the log discrepancy is going to be the same, but the S invariant, we have the equivariant version. So we just basically change everything equivariantly. So we change the valuation coming from the prime divisor E to the pseudo valuation with the group action G. And then we look at the, so originally we look at the vanishing order along E. Now we're looking at the vanishing order along E with the group action. So this is going to be the largest vanishing order with any group with any action of the element inside the group, and we still have the equivariant pseudo effective threshold, and we can form the equivariant beta invariance and J invariance as well. Similarly, Okay, and then basically everything will be parallel. And oh yeah, I also want to note here, if the divisor itself is G invariant, then we basically recover to the original notion previously in the usual evaluative criterion. And because we are looking at prime divisors coming from test configurations and prime divisors inducing test configurations, so we have this technical assumption where we consider divisors of finite orbit, and these are divisors which actually corresponds to equivariant test configurations. And we call the divisor a finite orbit if the action of the group on the valuation is finite. So we have only finitely many valuations if we take the G action on the valuation. Okay, then I have this result, equivariant valuative criterion. Basically, this is a parallel result of the evaluative criterion characterizing equivariant case stability. So the proof is very similar to the original one, and the statement is also very similar as well. Okay, so maybe let me just take a little, one more minute. So, if we focusing on, so for the equivariant evaluative criterion, we don't have restrictions on the group action. So if we're focusing on the finite group action, this is where we can take quotients. And if we look, we take the branch divisor correctly, if we take the quotient of a Fano variety, we get a log Fano pair by adding the branch divisor. And then we can also talk about the case stability of the log Fano pair downstairs. And then we can have the relation between case stability upstairs and downstairs. And this is exactly where we can what we use actually when I talk about the examples previously about finite covers. And also maybe let me skip this proposition, but to the main theorem here. So this finite cover trick is exactly where what we used, in fact, to prove the equivariant K-stability conjecture for the finite group case. Okay, and basically we pass to the quotient, and then we in fact we use the argument of the uniform YTD conjecture in Li Tianwang's paper, which is analytic, and then we try to pull back the K-line symmetric from downstairs to upstairs. So pull back K-line symmetric is easier, but pull back K-stability condition is actually hard. So this is kind of the key part in our proof. So yeah, I think I'm not going to go in details about the proof. So I think I'll probably just stop here. Yeah, thank you very much.
Thank you for the talk. Are there some questions or remarks or comments?
I have one question, if you allow me.
Mm-hmm.
Yeah, so I just want to know in general what's going on. So if I understand, if you consider a test configuration with G equivariant, you can resolve the singularities. So you can, you compactify it first and then resolve the singularities. And then you lose, it will be not polarized test configuration, but will be fiber-wise polarized.
Yeah, it's I think it's going to be what we call semi-test configurations. The
Yeah,
polarization
that's right.
on the central fiber is only semi.
So my question is the following. So can we expect, for instance, this uniform stability to be enough to test Ginian smooth polarized test configurations to get uniform stability or not? Is this any reasonable?
Let me see. I think it should be enough. If I remember correctly, yeah, I don't really have the result on the top of my head, but I think in Buxon, Hisamoto and Janssen's paper. Let me see. So yeah, so if we have a let me see. So maybe let's look at just the right half of the picture. So if I have a test configuration and I have a upstairs have a test configuration dominating this one, and if the polarized the polarization on Y is coming from the pullback of the polarization on X, then I think we have the comparison of the generalized Futaki invariant in the favorable direction, so that it's enough actually just to consider test configurations upstairs. Why? It's enough. So therefore, if I start with any test configuration, I resolve it, and I have a smooth test configuration, I can just consider, I think it's enough to just consider test configurations upstairs. Excellent. And I think this, yeah, I think this is also the reason why, in fact, right now, people tend to put the normality assumption in test configuration. In the original definition, I don't think normality is required there, but if I take the normalization, again, the direction of the inequality is in the favorable way, so that it's enough just to consider normalization, normalized test configuration as well.
Yeah, and then hence my second question. So in general, when you have a reductive group, we can also take the reduction, the GIT reduction of this smooth test configuration Y. And is it known what this Keller reduction of this object represents? Can we generalize your argument of taking quotients?
Yeah, I think in my paper with Yuchen, actually we have some arguments about when we have a finite group action, if we start with a test configuration of X, in fact, we can take quotients of the test configuration. So this is almost everything is perfect. So also because that, so basically we have a finite morphism between test configurations, and therefore because we have the, let me go to the definition, the intersection number. So the generalized Futaki invariant can be expressed as intersection numbers, so it doesn't change under finite map. So up to a multiple. So therefore everything is fine as well. So in fact, we use this trick a lot by taking quotients of test configurations. But of course, you have to maybe take some multiples of the polarization to have a linearization in the GIT quotient. Yeah.
Thank you.
And what about hypersurface? Can you come back? Is it still? I mean, what are the results in the direction of showing that hypersurfaces of low degree are K-stable? I mean,
I think let me see. So conjecturally, if I remember correctly, conjecturally we expect hypersurfaces of degree larger than or equal to 3 to be like this general one to be K-poly stable. I think this is the conjecture, and so for right now I think we have a lot of examples, especially the last year. I think that there's this method developed by Hamid and Zhuang using admissible flags, where they actually solved a wide class of concrete explicit examples, the K-stability of the explicit examples of Fano varieties. And but still, I think starting from fourfolds, we only know that smooth fourfolds, smooth cubic fourfolds are all K-poly stable. This is proved in Yuchen Liu's recent paper, where he basically shows that the K-stability notion of qubit 4 folds is coincides with the GIT stable notion, which basically generalize the results for qubit 3 folds, where in Yuchen Liu and Chen Yangshu's paper, they also again proves that for qubit 3 folds, K-stability notion coincides with GIT stability notion. And and in general, I think, we only have one direction, which is proved early, quite a long time ago, where we have the K-stability notion implies GIT stability notion. This is the only direction we know. So yeah, and let me see. So but yeah, so for other cases, I think that there are definitely a lot of cases we know right now, but there's still not a very systematic results in higher dimension about K-stability. But for hypersynthesis of hypersynthesis of higher degree, I think we have some results. For example, for hypersynthesis of degree in PN, for hypersurfaces of degree n, we know that they are all the smooth ones are K-stable, and this is done by computing alpha invariants basically. And there are also some results recently for higher degree hypersurfaces. We have K-stability results. Yeah.
And sorry, also, does your theorem has some kind of equivalent pendant in the just scalar setting?
Let me see. So, do I understand your question correctly? So, what? Sorry, what do you mean by the Keller setting? Do you mean the analytic side?
Yeah, analytic setting purely, yes.
Yeah, for the analytic setting, well, I think mostly the results is already included in the smooth case in data as Equivariant paper, because like in the analytic setting, they basically here, if we consider the smooth case, their result works for any.
I mean, sorry, I mean it's not anymore an integral Keller class. It's not anymore a line bond or polarization is not anymore. I mean, we don't have a polarization. We just have
I see.
Keller
So
class.
in that case, yeah, I don't think. Yeah, I'm not very familiar about those cases, and I don't think I have any inputs on that side. Yeah.
You know, after the results of Dervan, Dervan was also extending notion of K-stability to Keller classes, and other people did that also.
Yes. I think also in Dervan's result, I think recently he also tried to work with like the also for the not just the Fano case, for a general case, like also he defined the Z stability condition, which kind of related to Richland stability notion, very in some similar flavor. Yeah, but yeah, in that part, I don't think I'm very familiar with those parts.
Okay, very good. Are there any other questions, remarks, comments?
I have a small question about the divisorial instability. So have you tried to do that G-equivariantly?
I haven't really think about that question in detail, but I don't see any. I think things should be able to generalize to the equivariant setting.
Yeah, that was kind of what that's sort of. That's what it seems a very natural.
Right now, I don't see any
already,
obstacle in the generalization.
A reasonable, yeah.
Yeah, definitely. Actually, yeah, it's a good question because basically, my argument is very similar to the argument in Fujita's paper. So yeah, I don't see the reason why I don't see any reason preventing us from generalizing things to the equivariant case. Yeah.
And then one other small comment, the S invariant in your notation. So this interpretation as an expectation, I guess it can be useful for calculations. And that's just a small comment.
Yeah.
Yeah.
Yeah. Oh yeah. Yeah. Okay. Definitely. Thank you. Yeah, I think in reality, in a lot of cases when we try to, especially also when we try to estimate the S invariant, we usually want to write it in using integration by parts and get the so that we get this bound on the derivative of the volume. So yeah, that would be useful in reality as well, definitely.
Okay, very good. So there's no